Welcome to Mr. Rich's science class lecture on mineral properties. There are over 5,800 different minerals. Each mineral is classified by both its chemical composition, the elements from which it is formed, and crystal structure. The crystal structure is the pattern the atoms form when they lock together. Graphite and diamond are made of the same element, carbon, but have different crystal shapes, so are different minerals. The unique chemical composition and crystal structure affect a mineral's physical properties such as color, hardness, density, or how it breaks or reflects light. Additional testing for unusual mineral properties may help identify an unknown mineral. Sometimes complex tests are needed such as magnetism, radioactivity, acidic reaction, or X-rays. Minerals of the same species, such as quartz, all have the same X-ray pattern, although they may look quite different. Color can be an important mineral property. This is usually expressed as the main body color of the mineral, along with the intensity of this color. Some minerals are of differing color along different crystal axes, a phenomenon called pleochroism. If the color varies in two directions, the mineral is called dichroic, whereas if the color varies in three directions, the mineral is called trichroic. Some minerals are always the same color, such as copper minerals, azurite's blue and malachite's green color. But others can show a range of colors depending on different impurity elements or structural defects in their crystal structure. For corundum, chromium causes the red color in ruby, and iron and titanium cause the blue color in sapphire. Luster is another visual property of a mineral. This is the appearance of a mineral surface in reflected light. There is metallic luster like galena, or submetallic like hematite. Then there is adamantine. This is the brightest luster type, usually occurs in minerals with a high refractive index like diamond and is most sought after. Then there is resinous, a plastic-like luster such as sulfur. Vitreous has a glassy luster like quartz. Pearly has a shimmering, slightly iridescent luster like talc crystals. Silky is closely related to pearly but is slightly more dull, such as the mineral gypsum. The next is waxy, like jade. And finally is the earthy luster, looking like a dull, dirt-like clump like rusty hematite. Hardness. This is the resistance of a mineral surface to scratching. This is a simple scale of relative hardness, ranging from talc's hardness of 1 to diamond's hardness of 10. Determining hardness in the field is a very simple test, requiring the scratching of the unknown mineral against a mineral of known hardness. However, some minerals can be harder in different directions. An example would be kyanite. It is softer along its long axis. The Mohs scale has 10 common index minerals. Talc has the lowest hardness at 1 and everything scratches it. Gypsum at 2 is softer than a fingernail. Calcite at 3 is harder than a fingernail, but can be scratched by copper. Fluorite at 4 is resistant to copper and cannot scratch glass. Apatite at 5 has a hard time scratching glass and is easily scratched by a mild steel. Orthoclase feldspar at a 6 easily scratches glass and is scratched by hardened steel. Quartz has a hardness of 7. Cannot be scratched by hardened steel, and is able to be scratched by topaz or harder minerals. Topaz is very hard at an 8, is able to be scratched by corundum or harder minerals. Corundum is at a 9 and can only be scratched by diamond. Diamond is the hardest natural mineral at 10. Cleavage. This relates to the number, direction, and intensity of development of regularly spaced breakage directions of a mineral. It reflects differing strengths of atomic bonding in different directions in the internal atomic structure. Perfect, good, fair, poor cleavage is usually specified by its quality and its direction. Members of the mica group have one perfect basal cleavage. Some minerals lack cleavage, such as quartz, garnet, and instead have an irregular fracture surface. Pyroxenes have 2 distinct cleavages at 90 degrees. Amphiboles have 2 distinct cleavages at 120 degrees. Galena has cubic cleavage. Density and specific gravity. Density is the mass per unit volume, but is inconvenient to measure directly. Instead, we more commonly use specific gravity, a relative density in which the mineral is weighed in air, followed by a weighing while the mineral is immersed in water. The specific gravity is calculated from weight in air divided by loss of weight in water, expressed in units of grams per cubic centimeter. Streak is a property that is only useful to minerals softer than 6.5 on the Mohs hardness scale. This is the color of the powdered form of a mineral. It is a more reliable indication of a mineral than its main body color. It is usually tested by drawing the mineral across an unglazed porcelain tile, called a streak plate, to leave a colored streak. The streak plate has a hardness of about 6.5, and anything harder than that will not leave a streak. Another easily distinguishable property is transparency, also known as diaphaneity, is the degree to which light is transmitted through a mineral. Minerals can be opaque, translucent, or transparent. Another visually apparent property is the quality of the development of crystal faces present in the sample. Euhedral mean that there are well-developed crystals with most crystal faces shown. Subhedral is when only partially developed crystals with some crystal faces shown. And anhedral is when there are only irregularly formed minerals with no crystal faces shown. Crystal habit is another visually apparent property of a mineral. This is the three-dimensional shape of an individual crystal. Equidimensional can take on the crystal habit of cubic, equant polyhedral, spherical, equant anhedral. This habit is also known as equant. Inequidimensional displays prismatic, platy, tabular, lamellar, bladed, columnar, acicular, or fibrous crystal habit. Embayed crystals have hollows or embayments in their outer edges. Skeletal crystals have hollows or embayments in specific crystallographic orientations. Dendritic crystals consist of a regular array of fibers sharing a common orientation. Other common crystal habit terms are radiating, crisscrossing, reticulated, and botryoidal. The mineral property called tenacity is the toughness of a mineral. This describes the way in which a mineral can mechanically deformed before breaking. Fragile mean that there is almost no appreciable deformation before it breaks. Fragile minerals can easily be broken by cleaving along crystal faces like kyanite, or the fracturing randomly like sulfur. Malleable minerals can be flattened into sheets without breaking. Gold is a great example of a malleable mineral. Ductile can be drawn out into wires without easily breaking. Copper is the mineral that is most often used to make wire. Sectile is the ability to be cut with a blade into shavings. Gypsum and other soft minerals can be shaved with a knife. Flexible minerals can be easily bent without breaking, such as molybdenite. Elastic minerals can be bent, and when released, springs back to its original shape, such as thin sheets of mica. Conductivity is an important mineral property. Minerals can conduct electrical currents to differing degrees. Metallic minerals are good electrical conductors, such as gold, silver, and copper. Semiconductors are poorer conductors, like bismuth, antimony, and arsenic. Most non-metallic minerals are very poor conductors of electricity, such as silicates, carbonates, and sulfates. Some non-conducting minerals can develop an electrical charge when subjected to directional mechanical stresses, such as compression, called piezoelectric, or thermal stress, called pyroelectric. Natural piezoelectric materials include quartz, topaz, tourmaline group minerals, and Rochelle salt. Rochelle salt was the first material to exhibit piezoelectricity, discovered by the Curie brothers in 1880. Pyroelectric minerals, like tourmaline and quartz, are materials that generate an electrical charge when their temperature changes. Magnetism is another important mineral property. Some minerals can be strongly attracted, ferromagnetic, slightly attracted, paramagnetic, or repelled, diamagnetic, by a magnet. The most common strongly magnetic minerals are magnetite, which is iron oxide, and perovskite, which is iron sulfide. Some magnetite can be a natural magnet, called a lodestone, and can pick up small objects such as pins, or can act as a compass needle to find north if floated on a piece of cork on water. Some minerals can be radioactive and should be treated with extreme care. Some minerals containing uranium or thorium are radioactive and spontaneously emit alpha and beta particles, gamma rays that can be measured by a Geiger counter or blackened photographic film. Fluorescence is another identifying mineral property. Some minerals emit a distinctive color under ultraviolet light. An example would be the violet glow of fluorite, the green glow of willemite, or the pink glow of manganese-bearing calcite. This is usually performed by placing the mineral in an ultraviolet viewing box with a blackened interior in a darkened room. The color can also vary according to whether the ultraviolet radiation is long-wave or short-wave. Fluorescence is caused by small traces of impurity elements, called activators, in the mineral's crystal lattice. Some minerals have identifying characteristics that may be harmful to the researcher. Extreme caution should be used when using taste, smell, touch with a bare hand, and chemical reactivity. Some minerals have a distinctive taste, such as the salty for halite, bitter for sylvite. It is not recommended to do this type of test outside a laboratory or on potentially toxic materials. Some have an unusual feel, such as talc feels soapy to the touch. Others have a distinctive smell. There is a garlic smell when arsenic-bearing minerals are heated, or the rotten egg smell of sulfides when they are struck by steel. It is not recommended to do this type of test outside a laboratory or on potentially toxic materials. Chemical reactivity can give clues to a mineral's identification. The most common reactivity test is the use of dilute hydrochloric acid. It is used to test for carbonate minerals. When a drop of dilute acid is placed on a mineral sample, if it contains carbonate, it will react and release carbon dioxide gas, causing the sample to fizz or bubble, called effervesce. It is not recommended to do this type of test outside a laboratory or on potentially toxic materials. Fracture is the property of how a mineral breaks. Minerals may fracture in directions other than cleavage planes, when the strength of its internal atomic bonds is about the same in all directions. Fracture can produce curved conchoidal surfaces, or fibrous, splintery, jagged, hackly, or uneven surfaces. Minerals can be made of just one element, such as copper, or be a combination of several elements in a chemical compound. Minerals have a distinct chemical makeup and is referred to as the mineral's composition. The compositions follow simple rules of proportion. So pyrite iron sulfide has 1 part iron to 2 parts of sulfur. A mineral's composition can further be classified according to their chemical groups they belong to. They can be classified as native elements: sulfides, carbonates, oxides, borates, tungstates, chromates, halides, sulfates, silicates, etc. Chemical composition is usually determined with complex laboratory equipment such as X-ray fluorescence spectrometers, mass spectrometers, and scanning electron microscopes with spectrometer attachments. Small, handheld, portable versions of some of these have been developed for more convenient laboratory and field use. In conclusion, understanding mineral properties is crucial for identifying minerals, understanding their formation, and recognizing their diverse applications, from geological processes to technological advancements. By analyzing physical and chemical properties, we can gain insights into the Earth's composition and the intricate workings of geological processes. Thank you for watching Mr. Rich's class lecture on mineral properties. We look forward to having you back for our next video lecture.